Today we're going to continue with the radioactivity unit, and this is the 5th video in this series. In the last video we moved on to the Bohr model of the atom, so we looked at the arrangement of electrons in the atom and we learned what happens when an atom loses an electron to become an ion. In this video we're going to look at how electrons can change energy levels and how this gives us evidence to support the Bohr model of the atom. So just to recap from last video, electrons are arranged in energy levels and orbit the nucleus. Each energy level can only hold a certain number of electrons. The first one 2, the second one 8, and the third one 8. There are higher energy levels, but we didn't go into that. Now when an atom absorbs energy, the electrons can jump up to a higher energy level. The more energy that it absorbs, the higher energy level it can jump to. If an atom absorbs so much energy, the electron will escape, and this is when an atom becomes an ion. It has lost an electron. When an atom moves up to a higher energy level, we say that the atom is excited. The electrons in an excited atom will drop back down to lower energy levels over time. This can either happen really quickly or over a long period of time. When it does happen, it will emit electromagnetic radiation, such as ultraviolet, infrared or visible light, and so on. This is how neon lights work. The neon gas inside the bulb will be excited because we're transferring electrical energy to it. When these excited atoms de-excite, so the electrons fall down to lower energy levels, they will emit visible light. Now electrons can fall down to lower energy levels in different ways, and each different way that it falls down will release a different colour of light, and this is why we can get different coloured neon lights. We can see which electromagnetic radiation an element will absorb or emit by looking at a graph called a spectrum. A light spectrum, for example, will tell us all the different colours of light an element will absorb or emit. Let's look at the absorption and emission spectra of helium. The absorption spectrum will show us all the colours of visible light that will pass through helium, and it does this by shining a white light through helium gas, then using a device to detect which colours of light pass through this gas. We will see which colours of light that don't pass through because we'll see black lines in the spectrum, and these are the wavelengths of light that are absorbed. So the coloured line shows us which colours of light pass through the helium gas, and the black lines show us which wavelengths of light are absorbed. The emission spectrum is the opposite of an absorption spectrum, and they show us all the colours of light that helium emits. This is done by heating up helium gas so its atoms gain energy and become excited. As we leave it to cool down, the electrons will fall down to lower energy levels and light will be emitted. Again, we use a device that can detect this light and tell us which wavelengths of light are being released. So the coloured lines on this spectrum show us which colours of light helium emits. We use emission spectras in many branches of science. They're important in astrophysics, for example, because they can help us find out which elements make up stars, galaxies or nebulas. Another place they can be used is in forensic science, because they can help identify elements that are present, which can help investigations. But the important thing to take from this though, is that spectrums of elements are evidence to support the Bohr model. This is because we only can get them because electrons are moving between different energy levels.